Okay, this is the part 2 of vector review. Before going into the component form of vectors, there is a small aspect that we need to learn. This is x-axis and this is y-axis. A vector along the x-axis in the direction of the x-axis and a unit vector is called vector I. Okay, that is, this is what a unit vector along the x-axis is termed as, and a unit vector along the y-axis, which is vertically upwards, this is vector j. It's a unit vector. So I is a component along x-axis, unit vector, and j is a unit vector component along the y-axis. Okay, the same thing applies for 3 dimension. This is xy plane, this is z plane. So this any vector along the x-axis would be in the form of I, which is a unit vector along this direction, and the unit vector along this direction, as we have done before, is j, and the unit vector along this direction j is, z-axis is k. Okay, so k cap, I cap, and j cap, these are unit vectors along the 3 axes I, j, k, on I on x, j on y, and k on z. Okay, now how do we actually write a vector in 2 dimension with i's and j's? Okay, so just consider a vector like this. Okay, so this vector should be brought into this place like a position vector, which we have already done in the video of part 1. So once you put it as a position vector, and then you consider these 2 components, that is, this is the y component and this is the x component. So there are 2 x's here, that is 2 times I component, and we have 3 times j component. Okay, so this vector is actually 2I plus 3j. Okay, so you go this way and you go this way, this is vector 2I and this is vector 3j. So once you add these two, you will get this vector. Okay, so this vector is nothing but 2I plus 3j. Okay, you can also see that this is the point 2 comma 3. Okay, you can also write the vector in column matrix form like 2 3. Okay, so in general, if a vector starting from the origin reaches the point x comma y, then the vector can be written as xi plus yj, and you have a cap over this representing it as a unit vector, or you can also write it in column matrix form x y. Okay, so these are different ways of writing a vector in component form. So you need not bring it actually to the origin. Say for example, it's somewhere on the graph. You know that this is 2 units along the horizontal and 3 units along the vertical line. So placed anywhere, a vector can easily be termed as x y. You know how many unit vectors it has crossed over the horizontal line and how many over the vertical line, and then accordingly you can write the vector in column matrix or even in vector form. Okay, so if it was downwards, then it should be, this is negative vertical, and if it was like this, and this was positive horizontal. So horizontal positive is 3 units and vertical downwards is 2 units, which is negative 2. Therefore this is 3I minus 2j, and this is how a vector is written in component form. So this should be 3 minus 2. Okay, in a 3 dimensional, a vector has x, y, and z, right? All the 3. So what's x and what's y and what's z? Say for example, this point is x comma y comma z. Okay, and this is x units, this is y units, and this is z unit. Okay, so this vector is actually written in column matrix form like this, or in vector form like this, Cartesian form rather, because along z-axis k is the unit vector, and I for x and y for j. So xi, which is this vector, yj, which is this vector, and zk is this vector. Adding up all these 3, you will get this vector. Okay, so the component form is either in matrix form like this or in Cartesian form like this. How do you add, subtract, scalar multiply vector which is in component form. We have two vectors, okay, and you know what it is. This is vector 6 1, because 6 horizontal and 1 vertical, and this is 2 3. Okay, so what happens when you add them? So you just add them like this, and you should be getting 8 4. And if you use your this is 8 4, so your answer vector should be here, and you can use your parallelogram rule, and you see that it actually works here. Okay, so adding the corresponding components gives you the uh, resultant vector. The same for subtraction. Okay, so for subtraction, what do you do? 6 1 minus 2 3, so it should be 4 minus 2, and you can see that from here to here it is minus 2, and this is 4, so positive 4 and negative 2 for y, so 4 minus 2, as I explained just before this. And then scalar multiple. So if you have a vector like this, which is 1 2 3 horizontal and 2 vertical, so this is 3 2, and if I want to multiply this twice, so you can see that this is 1 2 3 4 5 6 and 1 2 3 4, so this, as the total is actually 6 4, and you can see that just multiplying 2 and 3 and 2 with 2, you get the result. So it is like k times xy is kx ky, and you can add x1 y1 plus or minus x2 y2, add or subtract the corresponding components to get the result. Okay, dot and cross product in component form. So any vector x can be written as, or a can be written as, a1i plus a2j plus a3k. Instead of x y z, I'm just using a1 a2 a3. And b, vector b can be written as b1i plus b2j plus b3k, and all these I, j, k's should have a cap over them to represent their they are unit vectors. Okay, a1 a2 a3 are scalar quantities, they are real numbers. Okay, what is dot product? We know that dot product is a dot b, right? In this form, in normal form, it would have been a b cos theta, but we don't know the theta between the two vectors. So what we are going to do is we are just going to multiply them, a and b. Okay, so this gives you a1 a2 a1 b1 plus a2 b2 plus a3 b3. Why are we getting this? If you multiply I dot I, that is dot product of two um, same components, I dot I, j dot j, and k dot k, and it's obvious that I dot I and I are parallel to each other, so cos 0 is 1, therefore this is modulus I. This again, we have done this in the first part of the video. Modulus I is 1, modulus I is 1, and cos 0 is 1. Therefore, the value of I dot I is 1, j dot j is 1, and k dot k is 1. And when it comes to I dot j, j dot k, and I dot k, you know that these are all perpendicular vectors. I, x, y, and z axis, they are perpendicular to each other. Therefore, I, j, k are also perpendicular to each other. Therefore, they are all equal to 0. So when you multiply a1i, b1i, you get a1, b1, because I dot I is 1. But when you multiply a1i with b2j, you get I dot j, which is equal to 0, and so on. If you multiply and see and apply these things, you will get a1 b1 plus a2 b2 plus a3 b3. Okay, what is cross product? Cross product is, if you have a cross b, it is a determinant when you write ijk, a1 a2 a3 and b1 b2 b3. Just find this determinant, and the value of this determinant with ijk would be a cross b. Okay, this is how you do cross product and dot products with vectors which are in component form. Angle between two vectors, you know that a dot b, or modulus of a dot b, is modulus a modulus b cos theta, right? So cos theta can be now found out by just rewriting them or rearranging them like this. So modulus of a dot b over modulus a modulus b will be the angle between the two vectors a and b, or in fact you can write theta equals cos inverse of. So the answer for this would be the angle between two vectors a and b. Equation of a line. Okay, there are three forms of equation of a line: Cartesian, vector, and parametric. Let's first start with vector product, vector form of equation of a line. Say we are given a line, a vector, say this is vector b, okay, and we are supposed to find the equation of this line. Obviously, this line is lambda times b, right? Because it is parallel to b, so it is some multiple of b. And say we are given a point a, and whose position vector is a, or even if the point is given, so you know that you can easily find out the position vector in the form of x1, y1, z1, right, as we have just done before. In order to find the equation of this line, we need a moving point P, which is we take it as x, y, z. And if you are able to find the position vector of OP as P moves anywhere on this line, we get the equation of the line as we do it in locus. Okay, now what is OP? OP is equal to, let's say take OP as R. Okay, so you can see that ROP is nothing but OA plus AP using the triangle law of addition. So OA is A and AP is lambda B, right? So R is equal to A plus lambda B is the vector form of a vector form of a equation of a line. Okay, now I used something like component form. So if I substitute R as x, y, z, and A as x1, y1, z1, plus say for B is I've got B as some x2, y2, z2. Okay, so this would be lambda times x2, y2, z2. Okay, so this is how we write an equation of a line, and this form is vector form. This is vector form, and this is parametric form because we are going to write this in parametric way. Let me tell you how it is. Just equate each component directly. That is, let the x is equal to x1 plus lambda x2, okay, and y is y1 plus lambda y2, and z is z1 plus lambda z2, and this is actually called parametric form. From here you can actually write it in Cartesian form. Okay, how do you write? From each of this you make lambda the subject, so x minus x1 over x2 is equal to lambda from the first, and y minus y1 over y2 equal to lambda, and z minus z1 equal to y3 z2 should be equal to lambda. So if you write all these three together, you'll be getting something like x1 minus x2 over x minus x1 over x2 equals y minus y1 over y2 equals z minus z1 over z2, and this is called the Cartesian form of the equation of a line. Okay, it should be noted that x2, y2, z2, which is actually the vector b, gives the direction of the line which we want. So this is called the direction vector of the given line. Okay, so this b is the direction vector, or in this case x2, y2, z2, the ones which are in the denominator gives you the direction vector. In this case the vector which is here is the direction vector, which is, this is more important for solving problems with equations of the line. Okay, now equation of the line from given information. There are two ways of information being given for finding the equation of a line. You might be given 2 points, or you might be given 1 point and a vector parallel to the line, as we just did. What do we do when we are given 2 points a, b? Join them. This is vector a, as we did before, and if you know what is a, say if I know that a is 2, 1, 3, and if I know that b is minus 1, 4, and 5, whatever some points are given, you know that the vector can be formed here, that is this b minus a, right? Minus 1 minus 2, 4 minus 1, 5 minus 3 would be the vector for this, right? The AB is equal to OB minus OA. We know that. So OB minus OA should be minus 1, 4, 5. OA is 2, 1, 3. And if you subtract them, you will get minus 3, 3, and 2. And this will be the vector which represents this direction. We can take it as B. in as we did in our previous case. So we know that R is equal to A plus lambda B, and A is 213 and B is just what we just found out, minus 332. So this is the equation of the line joining these 2 points. Okay, so what about one point and a vector parallel to a line? So you have a vector B and you are given one point A. So what you do is you need to find the equation of this line. Okay, so you find, you know what it is. When the point is given, you can find the position vector of the point. So this one is lambda B, and we know that R is equal to A plus lambda B, as we did before. Okay, angle between two lines. Just a few minutes back I said the direction vectors are very important to find in dealing with equations of the line. So angle between two lines are actually done as the angle between the direction vector. So if I have a line R is equal to A plus lambda B, or A1 plus lambda B1, and R2 is equal to A2 plus lambda B2, or mu B2, it will be different. The angle between these two lines would be the angle between B1 and B2, or in fact it is like cos inverse of B1 dot B2 over modulus B1 modulus B2. Okay, we use the modulus sign here. So B1 dot B2, this is the angle between the two lines. Okay, so you need the direction vector in each case, and then you know how to do this cos inverse. And these are some important concepts that come from the angle. If b1 dot b2 is equal to 0, which means that x1 x2 plus y1 y2 plus z1 z2 is equal to 0, that means they are perpendicular. If they are parallel, you'll have something like x1 over x2, y1 over y2, z1 over z2 will be a constant. Okay, that is, they have the same ratio. So if two vectors b1 and b2 have the same ratio of components, then they are parallel to each other. Intersection of two lines. So how do you find the point of intersection of two lines? Intersection of two lines. How do you find the point of intersection of two lines? Um, First of all, you write both the lines in parametric form, okay, with different parameters for each. As I just now said, maybe you can write R is equal to A1 plus lambda B1, and R2, the next line could be A2 plus mu B2. Okay, use some other parameter, lambda and mu. Okay, so use different parameters and write them in this form, parametric form. Not in this form, this is vector form. Write it in parametric form. Check if the direction vectors are proportional or not, that is b1 and b2. If they are proportional or not, you check them. If they are, then it is parallel, so you can't find the intersection of those lines. If they are not, then you proceed. Check if the dot product of the direction vector is 0, which means that they are perpendicular. So you are going to find the point of intersection of two perpendicular lines if b1 dot b2 is not equal to 0. Okay. Then equate the x, y and z of the two lines and solve the simultaneous equation. You know that x will be in the form of x1 plus lambda x2, and the other x would be x2 or x3 plus mu x4 or something like that. You know the numbers here, but you are only have to solve for lambda and mu. So you can actually equate them, x to x of this, like x3 plus mu x4, and y1 plus lambda y2 equals y3 plus mu y4, and you will get three equations with this. You have to solve them simultaneously and solve for lambda and mu. Okay, substitute the lambda and mu into those equations for x and y separately, for separate lines given. Check if both the answers give the same value. If they are, then they meet at that point. The value, when you substitute lambda, whatever x you get, whatever y you get, and whatever z you get, that's the point where they meet. If they don't give the same answer, then they are neither parallel nor they meet, that which means they are skew lines. Okay, here is a problem for you. You can try to solve this. Okay, what are the equations for lines on xy, yz, and xz planes? A line on xy plane, this is x, this is y, and this is z. Line on xy plane will have z equal to 0. Okay, so the equation of the line on xy plane is z equal to 0, and a line on zy plane is apparently x is equal to 0, and this would be line on xz, therefore y equal to 0. So these are the equations for those lines. Equation of a plane. Now we need two vectors and a point to find the equation of a plane. Okay, what do? We have two vectors, say maybe vector r and vector x and vector y. What we do is we move them to the point which is given. So these are the three things that have been given to us, and then we move them to that point, and then we take a moving point p, x, y, z, and then we make them all to lie on a plane. And if I can find out the position vector of OP, this is R, as we did for line, if I'm able to find the position vector, then I'm finding the equation of the plane, because P is a moving point all along the plane. So let's concentrate on how to find R. To find R, I need OA and AP. So if I get OA, which is A, which I know, which is given because A is a given point, A plus AP, OA plus AP would be my OP. So I can find OP, which is R, if I know OA and OP. I know OA, but what is OP? OP, you can see that it is actually part of the parallelogram formed by the vectors. Okay, say vector A, vector B, and vector C. Okay, so this is some, say, lambda times B, and this is mu times C. So some part of C and some part of B has been taken to complete to get this vector. Okay, so you can say that OA is A and AP is lambda B plus mu C. Okay, because this can be written as lambda B plus mu C. Okay, so this is the vector equation of a plane. Normal vector of a plane. What is a normal? Normal is some line which is actually perpendicular to the plane. This is normal. So how do you write a plane's equation in the normal form? Let's say there are two vectors and a point given, and as usual you move the vectors to the point and also move the normal to the point, and say the position vector of OP is what we want. As usual, this is R, this is A, and you need to find this is lambda B plus mu C, right? But what is this normal vector? This is perpendicular to the plane containing B and C. Therefore, this vector will be along the direction of B cross C. Okay, so this is B cross C. This line vector, which is normal vector, is B cross C. And we know that B cross C is perpendicular to AP, right? Or we can also say the normal is perpendicular to AP, is equal to 0. Okay, so what is AP? AP is nothing but OP minus OA. This is also done when we were talking about position vectors. Okay, so what is OP? OP is R and OA is A. So this is the equation we are going to get. N dot R minus N dot A is equal to 0, which means that N dot R is equal to N dot A. This is the vector equation of a plane in normal form, where we are using the normal vector to define the equation of a line of a plane. Sorry.